Welcome to my presentation on the automatic generation of digital calibration certificates in the vacuum metrology group of PTB. This is the work of Rolf Niebrecht and Thomas Bock, who in addition to their calibration obligations are also responsible for the IT infrastructure in our group. The vacuum metrology group is disseminating the scales for pressure below atmosphere and the scale for small gas flows below 10 to the power of -5 pascals cubic meters per second. For this purpose, a number of primary standards are operated. Membrane and spinning rotor gauges are calibrated with a static air expansion system, where a fixed amount of gas is expanded from a small volume into a much bigger one, and if the initial pressure and the ratio between the two volumes is known precisely, a well-known pressure is generated. At low pressures, outgassing dominates the uncertainty and a different method is used. This is a continuous expansion method, where a fixed gas flow is expanded into a volume that is pumped through a calibrated orifice. That's used for the calibration of ionization vacuum gauges. Reference leaks are calibrated by comparing their signal to the signal of a well-known gas flow from a flow meter by means of a quadrupole mass spectrometer, and similarly, reference leaks against atmosphere are calibrated. Over the years, the number of calibration was steadily increasing. Thus, an automated workflow was developed and implemented. Lately, the generation of digital calibration certificates was integrated into this workflow, and we started delivering digital calibration certificates to our customers in a test, in addition to the official calibration certificates, and have issued already 36 digital ones. So how do we do that? At the core, we are using the NoSQL database CouchDB. It's schema-free and based on JSON documents. That was done after a try with an SQL database already failed. That's because SQL databases are not very flexible with respect to changing the data structure, and that was not really compatible with the continuous development progress in the group. NoSQL databases, on the other hand, it's very easy to extend the data structure and also to change this, but on the downside, the user has to care about the consistency of the data, which in the case of SQL databases is guaranteed. But the extension issue was the more important issue for us. Each of the documents is a self-contained data set that does not depend on other data sets, unlike an SQL database. So CouchDB is open source. You can just directly download this and try for yourself. Unlike an SQL database, you can start directly without defining any schema. Another nice feature of CouchDB is the multiple master replication process. That means all instances of the database are masters, there are no slaves, and if one instance is corrupted, it can be restored from any other instance. At the vacuum metrology lab, an instance of the database is running on every measuring computer, and 2 instances are running in the data center, one serving as a backup. An additional layer of documentation and backup is added through versioning of the database with Git. Other tools that we are using is the Ginger library in Python that we use as a template system for the generation of text files from text blocks with placeholders for the variables. So that is needed when we want to generate LaTeX files that can then be compiled to PDF, XML files for the digital calibration certificates, and also HTML files that can display information in the browser. The user phases are done with HTML and JavaScript, and so they can run in every browser in the lab, so that's the advantage. Generally, we try to implement functions as web services to keep them slim and focused on one task. For example, the template system is running on a Flask server, also done with Python, and can be accessed via the HTTP protocol. So you send a JSON document to it and you receive an XML file, for example. HTTP protocol is suited because it's a stateless protocol. That means that it does not depend on the history of the events, and that reduces complexity, and that's also the reason why it's used for the internet. We are also using other servers, for example, Node.js server for the communication with the measuring devices, and of course the database itself is also a web server. Let's have a look at the JSON documents. JSON stands for JavaScript Object Notation. It's a hierarchical key-value data structure, and you can see one document displayed here in the web interface of CouchDB. It's a calibration document where at the highest level you have the key calibration that then contains keys for the customer with all the customer data, and for the measurement where you have a key for the values and another key then on a lower level for pressure, for example. At the lowest level you have a list of the values of pressures used in this calibration. This is also shown schematically here, calibration at the top, and then splits into sections for measurement, analysis, results. Each of those sections splits into sections like values, for example, data, and then the values splits into date, temperature, and pressure, and so on. So you see that it's easy to extend just by adding additional sections, and if you modify the data in one section, all the other sections are not modified, and that's how you keep track of the consistency of your data structure. JSON is directly interpretable as JavaScript, so that's good for web applications, but it's also easy to use in many other programming languages. For example, in Python it's mapped onto a dictionary object. It's human readable, as you can see here, and for us it's important that because the CouchDB documents are JSON documents, so that's important for us. Here you can see a user interface done with HTML and JavaScript, so it runs in every browser in the lab. This is used for the planning of calibrations, where customers are selected from a list, and the type of calibrations and the calibration devices are selected here. This website is actually served by the CouchDB because you can attach HTML and JavaScript files to a JSON document, and that's a nice feature too. Here you can see a user interface for the generation of calibration certificates. You can go through the different sections of the calibration certificate, and then you can swap the different text blocks around. Let's have a look at the workflow. At the center you have the database and the JSON documents. We start with customer documents that contain information on the address and lists, and the documents for the type of calibration. These are selected during the planning, as you were seeing just before, and these two information are then merged into a so-called planning document that then contains this two information. From this we can generate an offer via the template system, generating a LaTeX file that is then compiled to PDF, and once the customer places their order, confirmation is generated in the same way. And the planning document is split then into calibration documents, one for each of the devices to be calibrated, and all of the documents contain the information that was there in the planning document before. Then the measurement receives the values from the calibration document, so on the pressure points, for example, at which calibration should be carried out. Then the values are measured and written into the section for the measurement. Measurement programs are written with LabVIEW and Node.js at the moment, and also Clojure. And then in the next step, the analysis program reads the data from the measurement and writes back their results to the analysis sections. Analysis programs are done with R and Python in our case. During the analysis, information is needed on the calibration data for the devices used for the measurement. That is collected from the database from so-called calibration object documents that are then collected during the analysis and merged into the calibration document. Used during the analysis and merged into the document so that all the data that was needed for the calibration is contained into this one document. Then from here, the calibration certificate is generated through the template system, first making a LaTeX file that is then compiled to PDF, and through the same template system, the XML file for the digital calibration certificate is generated. Let's have a look to the measurement again. Communication of the measuring programs to the measuring devices is not directly carried out, but it's carried out via a Node.js server that we call a relay server. It runs as a web service, and you talk to it via the HTTP protocol. It facilitates simultaneous readout of all the devices during the measurement, and it provides a standardized interface for the various different protocols of the measurement devices. And we are happy to announce that we have received our first digital calibration certificate for a voltmeter calibrated at CleverLab, which is the calibration facility, an internal calibration facility at PTB for electrical quantities. The voltmeter had 8 channels and was calibrated between -10 to 10 volts. The result table had 500 entries, so that's something that you don't want to do by hand, and they have provided us with a digital calibration certificate that we have then converted to JSON and uploaded in our database, where it can now be used during the analysis when this device is used. Finally, some overview and outlook. So the vacuum metrology group is calibrating a number of devices. The relative proportions are shown here. We have a lot of capacitance diaphragm gauges, spinning rotor gauges, ionization vacuum gauges, and test leaks against vacuum and atmosphere. We have implemented the generation of digital calibration certificates for the capacitance diaphragm gauges and also for the spinning rotor gauges. And we have started to routinely issue test DCCs in addition to the official printed calibration certificate this year. And for the next year, we also want to implement the digital calibration certificate for the remaining devices and routinely issue DCCs for all calibration devices. We have also provided examples to the repository of the XML schema at the GitLab server of PTB. If you want to have access, you have to write an email to Siegfried Hacke, and there you can find our two examples, one for the capacitance diaphragm gauge and one for the spinning rotor gauge. Thank you very much for your attention, and you can type in your questions in the Slido window next to the talk, and I will answer them during the conference.